Welcome everybody to the FCC seminar. We are happy to have Amey Bhangale. Amey is a frequent visitor here. Amey did his PhD at Rutgers with specific to party and has had stints at Weizmann, KTH, the Simons Institute, and is currently faculty at UC Riverside. He works on a variety of problems related to hardness approximation for reachable proofs. He'll be taking on one of the very exciting set of work that he has been working on the last couple of years on approximability of satisfiable constraint satisfaction problems and applications.
Okay. Thanks for that one introduction. I'll be talking about constraint satisfaction problems. And so this talk will be based on joint work with Subhash Kod and Lower Minzer. And so we have like some series of papers. And so this talk is basically trying to tell you the story of what this series of papers is about and what is it that we have gotten up to this point, and maybe some overall there. Okay. So the agenda for this talk is I'll define CSPs, constraint satisfaction problem, and I'll define the problem of approximability. And then to understand the definition better, one motivating example of CSP that we'll spend some time on is linear equations going on different CSPs, and then I can state our results from paper 1 and 2. And then I want to spend some 10-15 minutes on the techniques, but here I'll be very hand-wavy. I won't define a few things, but just sort of give the high-level idea of how to prove the results that I'll be mentioning. But towards the end of the talk, I'll mention one stability result, which is a standalone result, and that I'll state formally. So if you don't understand some terms from these techniques, you should be able to understand this statement of this result. And then I'll give one application of this result, which is an application to additive commutator. So let's start. So there are these well-known CSPs. T-sat is a well-known CSP. Here the variables are Boolean, and each constraint is all of 3 literals. And you are given a collection of constraints and variables, and you want to find an assignment that satisfies as many clauses as possible. 3XOR is again a 3 CSP theory because there are 3 variables involved in each constraint, and each constraint is XOR of 3 variables. And is each constraint is AND of characters. Okay. But again, the task is to find an assignment that satisfies as many constraints as possible. Okay. So these are like different predicates. So this is the SAT predicate, this is the link 3XOR predicate, and this is the K AND predicate. So let me define the max CSP problem in general. So we are given a predicate which is just a set of assignment from this set sigma to the case. Sigma is an alphabet. Okay, so think of sigma as some finite alphabet, some size 10, size 2, and k is also finite, some constant number. And this map just gives you the set of satisfying assignments. And we have a set of variables taking value from the domain of sigma. So abstractly, I can define each constraint as this predicate applied to a tuple of k variables. Okay, so each constraint looks like this. And so here, a variable, it can be a literal. For example, 3 SAT, you can plug either xi or si complement. So we can define literal for general domain, but I won't define it for now. But what we need to just think of is that without looking, even that also makes sense. So these constraints are of these types, and again, the goal is to find an assignment to these variables that satisfies as many constraints as possible. And the constraint is satisfied if this evaluates to 1. So for 3 SAT, this map is mapping all 3 bit strings to 0, 1. The only 0 mapping is the 0, 0, 0. Because 3 SAT has 7 side string assignment out of 8. And for XOR, this is like parity. So it maps odd parity strings to 1 and it maps even parity strings to 0. So the value of the instance, so given an instance, the value of the instance is the fraction of satisfied constraint at this assignment, and we are interested in finding the maximum value. So the problem also makes sense if you actually want to find an assignment, as well as if you just want to conclude, the value of this instance is 0.5 or 0.7. So, in this series of paper, we are interested in characterizing the approximation threshold for CSPs. right? So, so if the instance
P is the predicate.
P is the predicate. So yeah, in this, yeah, P is always the predicate. So once you fix a predicate, it defines your problem. If you fix 3 sat, it defines your max 3 sat problem. And then you can talk about, whether you can find a satisfying assignment in polynomial time, or whether you can find the optimal assignment in polynomial time, or whether you can find some assignment which is close to the optimal assignment. So by characterization of this approximation threshold, I mean that if you are given an instance which is C satisfiable and C is at least S, then can we find an assignment that satisfies at least S fraction of the constraint? So this is a weaker rule, right? So the ideal rule would be, if you are given an instance which is C satisfiable, give me in polynomial time an assignment that satisfies C fraction of the constraint, right? But this is a weaker goal depending on how small S is. So this is what we want to understand. Does the question make sense?
So to the problem, C and S are both problem. I mean, C and S are some fixed number, they're not part of the input.
They are part of a problem.
They're part of the problem.
Okay, so I can give you CS. So CS max PCF. Right. So here you are always guaranteed to so the input always has an assignment that satisfies the fraction of the constraints, and here you want to find an assignment that satisfies as many as possible, and we are happy if you give me an assignment that satisfies S fraction of the constraints.
The green, there's no color. The green and red there, I have to do the green and red here.
The green and red, no, that has nothing to do with this. So it just means that you are given an instance whose value is somewhere here, and then you want to find something over here.
Okay.
So C is referred to as the completeness guarantee and S is the soundness guarantee. Okay, so let's look at the C and S, these parameters for these certain famous predicates or well-known predicates. So one is the 3 sat, and the predicate, as I mentioned, is all of 3 literals. And here, suppose you know the guarantee that your instance is satisfiable. Of course, it's NP complete. I mean, it's NP hard to decide whether the instance is satisfiable or not. So what can you do? In terms of finding an assignment that satisfies as many constraints as possible in polynomial time. Right? So the very simple algorithm here is just output a random assignment. For each variable xi, set it to true with probability half, and set it to false with probability half. Okay. Now, if you fix any constraint, the probability that this is satisfied is 7 or 8, because there's only one 0, 0, 0 assignment. I mean, if all the literals are positive, then there's only one assignment. Doesn't matter. So here there is only 0, 1, 0. That's the only assignment that falsifies this clause, and the rest of the assignments they will make this clause true. So this simple algorithm, it satisfies 7 or 8 fraction of the constraints or clauses in expectation. And you can de-randomize this, and you can actually get a polynomial and deterministic algorithm that satisfies 7 or 8 fraction of the constraints. So regardless of what the guarantee on the instance is, you can always find an assignment which satisfies 7 or 8 fraction. And this is shown to be tight. So Hustler, in his famous figure, he shows that this algorithm is tight. You cannot do better than 7 or 8 in polynomial time. So assuming P not equals to NP, you cannot beat this 7 or 8 approximation for 3 sat.
And that 7 over 8 plus some constant epsilon.
Yeah, so whenever I say that you cannot beat this, it means that it's NP hard to find an assignment that satisfies this fraction, this fraction of the project for every constant epsilon greater than 0. So epsilon will be any time. Okay. For 3 being over an abelian group, think of this as just F2, plus your Boolean XOR, or any abelian group. If the instance is satisfiable, then you can actually find a satisfying assignment in polynomial time. This is sort of the Gaussian inversion sort of thing that you can do. Okay, so I mean, it's defined over a field, but you can also do it over groups, and that works. Okay, so for satisfiable instances, you can find a satisfying assignment in polynomial time. But if the instance is almost satisfiable, if the only guarantee that you have on the instance is if it is almost satisfiable for any small constant epsilon, then the best thing that you can do is just give a random assignment. So random assignment satisfies 1 over g fraction of the constraints, and Haskell told that this is the best that you can do in this case. Okay. So the important distinction which we'll be interested in is what happens when the instance is satisfiable versus what happens if the instance is almost satisfiable. Right? So the kind of guarantee that you can achieve in polynomial time, it changes drastically whether the instance that you are given is satisfiable or almost satisfiable.
That is for some epsilon or arbitrarily small.
This is any constant epsilon greater than 0. You can set that to be any constant. 0.9999 satisfiable instance, you can't do better than 1. Unless p 0. Does that make sense? And so again, I'll spend some time on this predicate. So this predicate is the same predicate as that, but over a non-abelian group G. So here constants look like x, y, z is equal to some group element C. Okay. And here the same result for this holds. If the instance is almost satisfied, we can't do better than random assignment. This was shown by Engelbertson, Holmerin, and Russell. But
So in both the second and the third column, we are thinking of G as some fixed finite.
yes. So whenever I talk about predicate P, this is fixed. This is like fixed, a constant. Right. So I should mention, yes. So I define a problem max ceiling over a non-abelian group G. So that is the problem. So G is fixed and its size is some constant, like 5, 10. And then we look at a CSP where every predicate is of this type. Okay. So the same result holds here. You can't do better than random. But surprisingly, if the instance is satisfiable, then you can do much better than a random assignment. So the approximation factor that one can ensure, and I'll give you this approximation algorithm. It's a very nice algorithm. It's 1 over size of the commutator subgroup of a group. Okay, for some groups, this size is much smaller than this, so this is much better algorithm than this algorithm.
Why do you say surprise? Because the upstairs for abelian group, you had the same phenomena, right? I mean, even more striking.
Right.
So why is this?
So surprising in the sense that the answer is not 1 over G, the answer is not 1. So.
Oh, surprisingly, this is tight.
And yeah, so we show that this is also tight, assuming P is not equal to G. Right. So there's a simple algorithm. We'll see the algorithm, and then we show in 21 that this. What is the
what is that number? D comma.
So this is the commutator subgroup of a group
Of G, yeah.
of
The size of the commutator.
the size of the commutator.
This is a case where both the upper and the lower bound are not trivial.
Yes, here both the upper. So the upper bound is a folklore algorithm, and the lower bound was not very close. Yeah. Lower bound is showing the NP hardness.
So in both the 7 by 8, 1 by G, so we know that 7 by 8 plus epsilon for any constant epsilon is not achievable, and if P not equal to N.
Yes.
But like, is it interesting to think of an epsilon could be some diminishing, like 1 by log?
Yeah, even those questions are interesting. In fact, here you can put epsilon to be 1 over polylog n or something.
And still it's
No, 1 over log. Okay, 1 over log. But you show 1 over polylog for 3x or 3x. Okay, so for 3x or you can set this epsilon to be 1 over polylog, and that is still NP hard. NP hard stuff. You want to do that? That's NP hard or don't? Okay. So I mean, yeah. So it depends on two factors. Whether how efficient your reduction is, and so on and so forth. But if you use the same reduction and use some stronger starting hardness result, then you can set that epsilon to be some little low one. Okay, but as per mentioned, the little low one can be 1 over log n. In some cases, here you can set that to be 1 over polylog. I think that's it. Okay,
So I just want to. So here, in instances when, for example, let's say the commutator subgroup was basically the entire group.
Yeah.
Okay. In this case, it's like saying whether or not it is fully satisfiable
Yes.
or almost satisfiable, the best you can do is one
that
energy.
Yes. Okay. Okay, so again, coming back to the question, we want to characterize the approximation threshold for every CSP. Given a satisfiable instance, we want to understand what is the largest S with which you can come up with a S satisfying assignment. Right? I mean, as you lower down your S, your problem gets easier, right? So, and there's a lot of success in understanding these characterizations. And this is a famous result by Amey, which says that So we know precisely what, for every P, we know precisely up to which S you can approximate a max PCSP. So let me state, so.
The red button will
No, then it's. So for every max PCSP, you can define something called semi-definite program, which I won't define in this talk. It's some relaxation. It's like some stronger relaxation than the linear program that you write for your combinatorial optimization problems. And then you can talk about the integrality gap of this problem of this relaxation, right? So what is the integrality gap? Suppose I have an instance I, and then suppose this integral value is S. There is the optimal assignment satisfies S fraction of the constraint. But since the SGP is a relaxation, it can give you a higher value. So it's a relaxation. So let's say the SGP value for this instance is C. Okay, so this means that this is the CS integrality gap for this max species. The integral value is S, but the SGP says that the value is like slightly higher C. Right? And so what Raghavendra result says that just give me one instance which exhibits CS integrality gap for max PCSP, and I can take that instance and convert that into a hardness result. Okay. So give me an instance. So for example, for CSAT, if you give me an instance with value 708, but the SGP value is 1, which is like 1708 integrality gap, then I can take this instance. Doesn't matter this instance is on 10 variables or 50 variables or 100 variables. I can take that instance and feed that into some reduction, and that tells me that if your instance is almost satisfiable, then you cannot beat this approximation. You cannot find an assignment that satisfies more than 708 factors.
So this will talk about a specific kind of SDP relaxation.
Yeah, it's some basic SDP that you can write for max.
Basically saying some of those SDPs are the best.
Exactly. So Raghavendra's characterization says that those SDPs, what are the approximation algorithm that you get out of those, that is the best that you can do, assuming unique games architecture. Okay. To state it more formally, so if you give me a CS integrality gap instance of max PCSP, then it is NP hard to find S plus epsilon satisfying assignment, even if the instance is C minus epsilon satisfiable for any constant epsilon greater than 0.
What is P here?
What is
P?
P is the predicate.
P is P can be anything.
P can be anything. So choose the predicate of your choice. Give me this integrality gap instance. Then you can just feed that into a reduction, and that will give this NP hardness result, assuming you can.
But given the predicate, the SDP is also fixed.
SDP is always fixed. Yeah, the population is always fixed. It's like a linear. Yeah, it's like a program that you. And there's also
This Raghavendra result, model of the fact that unique games conjecture is very UGC hardness. The subsume all the results which you flashed on the previous page.
previous page, those results were NP hardness.
No, but
yes, it's
if
a
you
proof
are
of-
willing to go to UG hard, relax
Yes,
at UG
yes.
hardness.
So there are very easy ways to construct integrality gap instance. That is for this 3-SAT, max lane, and all.
Even non-abelian group.
Even non-abelian, I expect, yeah, you can construct one over size of G.
Okay.
And then you can just get this asymmetric games. Okay. And this is optimal because there is a matching approximation algorithm. Right? Just the FTP, you can somehow use some SDP rounding algorithm that matches this approximation factor. Okay, so this is what I mean by characterizing the approximation threshold for every CSP. So, and this is not a definitive character. So if you give me some weird predicate and ask me, what is this for almost satisfiable instances, what is S for which, it is NP hard, I won't be able to tell you. I mean, I have to like brute force over, if you ask me this, suppose I don't know the result about CSAT. And if you ask me, for CSAT, what is the best soundness that you can get? Okay. So this characterization does not tell you that, because this characterization relies on existence of some integrality gap instance. So you have to maybe brute force search over, instances and find an instance with 1/708 gap, and that tells you this, that gives you this hardness. What I'm saying is that this is not explicit, but still good enough characterization.
So I'm getting confused. So I thought that you were saying that there is a prescribed SDP.
Right, yes.
And what you're saying is there is a inherent algorithmic difficulty of determining the integrality gap of that ST.
Yes, yeah, yes.
And
You
that
can't-
is why this is,
Yes, yes.
that is the
Right.
unsatisfactory.
That is why this is not explicit. The predicate is very small, right? I mean, it's like, you just use this function from sigma to the k to 0, 1. So you expect, there may be some simple algorithm that spits out the best S that you can find for a given C. But yeah, that algorithm is not, we don't know that.
So
We don't even know whether that's comparable.
It's you search in a small space, so you should be able to get hold of this.
That is also not
Not
sure. That is also not clear.
Small space. You tell me epsilon, and now I know how large size this object I need to go to and.
Probably that you can do, I think. Yes,
Hmm.
you can do that. But the exact constant
You
is
want the
undecided.
exact C index, but
It's supposed, it's believed to be undecidable.
So, still trying to parse this. So, okay, so we have one SDP based on the max PCSP that we have.
Yes.
And now maybe there's a specific instance that I have where the SDP value was C. And but on the other hand, the actual integral value is just S.
Yes.
So that gives you one integrality gap.
Yes.
But maybe I have another instance where the SDP value is C prime and the integral value is S prime.
Yes.
And
the same hardness. You get the hardness for C prime S prime now.
But is there a way
max
one?
over almost the
So
integrality gap
sometimes these are not comparable.
What? Because it could be like this, right?
So if your C prime is here and S prime is here, and let's say your C is here and S is here, you get two hardness results if you plug this.
Yeah, but it's
okay.
That's what I want.
Very
Okay.
So one thing you can do is, you just restrict yourself to SGP value 1, then you can ask. You will give me an instance whose integral value is 0.7, so it gives you 0.7 hardness result. But maybe someone can come up with a better integrality gap, 0.65. So you get what is the best integrality gap you come up with? Let's say you take C value 1. Oh, that's the hardness result. Okay.
So this is the existence of this integrality gap, and it implies this. So there is not an infinite.
There is no infinite. Yes. Wait, integrality gap implies this.
So, what do you mean by there is a matching approximation error?
So this says that if you give me C minus epsilon satisfiable assignment, it's hard to find S plus epsilon. There's also an algorithm that says that if you give me a C satisfiable instance, if you give me an assignment that satisfies S plus epsilon.
But why is it not an even? No,
Then
I mean, somebody asked if it's an even only if. I thought it is, right? I mean, from the so suppose I fix this SC, right? Then basically, I mean, there is a polynomial time algorithm,
Right.
even only if.
Right. Actually, yeah, you're right. Yes. With the polynomial time algorithm, if only that you don't have that integrality gap instance.
Yeah.
Worse than that integrality gap instance. Yes.
So it is a character.
It is a character. Yes. It is even only.
So finding, so for any S, C, S, finding an S plus epsilon satisfying assignment, even if the instance is C minus epsilon satisfiable for everyone. If this is LP hard, then there must exist some basic SDP relaxation where the integrality gap is C, S.
Yes, I believe yes, that is true. I think how much time I have? 5.
I think we are.
Okay. So now here comes the main point of the kind of problems that we study. So this result is very nice. It gives you full characterization. Earlier results, people used to take one predicate, true hardness for that, 3 that, then Boolean and this. Whereas this result just like gives hardness for every predicate and gives characterization for every predicate, right? So we want to do some certain characterization, but everything is known. So what is it that is remaining, right? So the thing that lacks that is not good in this hardness result is that we can't say anything about satisfiable instances because you always lose epsilon in the hardness result. So this result won't be able to tell me if I give you a max C set which is satisfiable, what is the best that you can do. And that was the reason in the table that I showed, there's a difference between almost satisfiable versus satisfiable. And in this work, in the series of works, we are trying to find characterization when the instance is completely satisfiable. Okay, so is the question clear? So the question is characterize the approximation threshold for every satisfiable CSP. If the instance is non satisfiable, then can we find an assignment that satisfies at least S fraction of the constraints and in polynomial time, and how far can we push this S? Can we get the some characterization for this value of S for every predicate? Yeah, so that's the same question. Again, for 3 side, this value of S is 7 or 8. For 3 in this value of this is 1 or side of the committed surface. And this question is really difficult because if you could answer that question, you would have solved the dichotomic conjecture, which people have solved recently, but it was a big conjecture in this area, right? Because the dichotomic conjecture says that given a predicate P, just decide whether checking satisfiability of max PCSP or PCSP, whether it can be done in polynomial time or whether it is NP complete. Okay? So this is same as saying that whether that value of S is whether that is less than 1 or is equal to 1. Is equal to 1 doesn't make sense. It's just that for a given predicate, whether the S that we want to find, whether it is less than 1 or not. If it is less than 1, then that means that the PCSP is NP complete. Otherwise, it is NP, right? So if you could solve this question, you would have solved this dichotomic conjecture, which is essentially proven by Golotov and Chu dependent. Right? So at least we know which predicates it's hard and which predicates it's easy for checking satisfiability. So the next step is find optimal S for every predicate. Right. And this is extremely non-trivial question. So I had just one slide for one predicate. This is an NGW predicate. I don't know. Yeah, not to one predicate. So the setup, so this is a clearly predicate over a Boolean variable, and the set of satisfying assignments are various. Everything except not to ones. Some arbitrary predicate.
It's a weird acronym.
Yeah, so I don't know who named it.
The W refers to the W is a part of the 2, or is it like 1?
I don't know. Maybe, so I don't know whether they meant this or not. I just made it up.
Oh, okay.
It isn't not two whites. I don't know.
Oh,
I think I just made it up, not two ones. I mean, it is the predicate not two ones. I don't know why they name it, why they call it NTW. Why not NTO? Okay. So just the history of what happened for this predicate is the random assignment gives 5, right? Same argument as 3 sat because there are 5 accepting assignment out of 8. And so the optimal NP hardness for on almost satisfiable instances, this was again showed by Husser in his same paper where he showed the 3 sat hardness. But it's almost satisfiable. Then we had NP hardness with this factor. So the S value for this predicate was proved to be less than or equal to 20 or 27. Then O'Donnell and Wu, they gave a dictatorship test, which is sort of a gadget in a reduction with optimal parameters. Okay. And then they also showed conditional hardness result on satisfiable instances, which is what we want to get. And then finally, Husser closed this thing by giving optimal NP hardness. Even if the instance is satisfiable, you can't do better than you can't get an assignment to satisfy more than for your fraction of the constraints.
Kind of great question. But when we want to find like this goal of trying to find an optimal S for every set, what kind of answer we are expecting?
So that means a sort of answer. Just give me
something that some general meta theorem that applies to.
Yes. As I said, I mean earlier people used to take one predicate and just show it for that, but then now we have this fragmental result, so we should ask. I mean we can ask for more. Why just study one predicate? Why not just prove a theorem which is in full generality for like predicate?
Two questions. So one is it's not 2. That's the reason. The acronym is due to O'Donnell and
is it? Okay.
Wu, and it is short for not 2.
But TW is 2.
Okay.
2. So I didn't know that. Okay.
And
I always thought that is not 2 whites, but
questions for the question. So the previous slide you showed that a statement of this will imply the dichotomy theorem. So
if you know this for every predicate.
We know it for every, if you characterize it for every predicate, you get the dichotomy theorem. But of course, now you have the dichotomy theorem.
Of course.
So just dichotomy theorem and Raghavendra don't give you a.
Raghavendra, you are bound to do epsilon. Because anyway you're using unigames conjecture, so
Okay,
you lose perfect completeness, like or satisfiability you lose as soon as you use unigames conjecture as your starting point.
okay.
So you won't be able to say anything about satisfiable instances. And dichotomy just gives you, whether that value of S is less than 1 or not.
But it is principle conceivable that, of course, it implies a dichotomy theorem, but it's conceivable that there is a simple proof of this fact by assuming the dichotomy theorem statement and some Fourier analysis.
Sure, yeah, I mean, it's conceivable.
It's conceivable,
But yeah, I mean, in general, proving hardness result for satisfiable instances is like really, it's really difficult. It gets into all this Fourier and whether you can control some terms and not, and those are very difficult.
okay.
So another thing, so for this one, you can expect an answer. No, not just for this, but this 1 comma
Yes.
question without the unique games conjecture, right?
No. So we also have to rely on some conjecture.
No, why is it clear? Because I'm saying that the Raghavendra thing is slightly incomparable here, right?
Yes.
So the fact that the Raghavendra thing has not yet been proven just based on NP hardness
Yeah, you
doesn't necessarily imply that this one also will have to go via the unique games conjecture.
No, these are incomparable problems. Yes.
So I thought his point was that you probably don't want it to go via unique games.
Yeah, unique games, personally, unique games, you don't have a satisfiability guarantee in the
Right.
Yes. Okay, so coming back to this table, so we are really interested in these two rows, and what really helped in these two cases compared to these two cases is that the algorithm uses some sort of linearity property of a predicate. Here it's obvious, right? The predicate is linear. We can do something called Gaussian elimination, right? And here I'll show that here also this non-trivial approximation algorithm uses some linear property of this predicate, which I'll define. Going really slow. Okay, so that's coming to this motivating example.
The last row, what is the other? It's P not equal to N.
Yeah, so this is purely P not equal to N. Yes. So before this, nothing was known. This was only the that was known. We gave NP values for this. Okay. So these are the blue slides. Those are just for the algorithms. Motivating example. So what is it? Again, I mean the equations they are of the form x dot y dot 3 is equal to 1 or meaning two constants. This is non-abelian group operation. You fix the group G, and that's our predicate. Right? You can apply the sort of constraint on a tuple of three labels. So let's look at a few definitions. So for element G and H of a group, the commutator of G and H is defined by this element G inverse H inverse GH. I mean, if G is abelian, then you always get 1. But if G is not abelian, you get 0. So commutator subgroup is a subgroup generated by all the commutators. Just an example, the commutator subgroup of G and Q, which is the invertible n cross n matrices over FQ, is S and Q, which is invertible n cross n matrices over FQ, but with determinant 1. A commutator subgroup of this Sn, which is just the permutation group, is alternating group, which is all even parities, I think. All even parities. I mean, not parity, permutation. The permutation can be even or odd. So An is the set of all even parity permutation. Okay, and now this is an important trick called abelianization, which is if you quotient this group by the commutator subgroup, you get an abelian group. Okay, an example. So if you quotient G and Q by Sn and Q, you get FQ star, the multiplicative subgroup of FQ. If you quotient Sn with An, you just get 0, 1, the FQ star. Okay, so is this?
You get F2, not F2.
No, you get F2, yeah, that's not FQ star because it's 0, 1. Okay, and the picture looks like this is your whole group. This is your commutator subgroup. There are two elements here. Now this is your quotienting. And now if you multiply this and this, you get that. And this is an abelian operation now on the quotient. And this is the smallest. So one important property of this commutator subgroup is that it's the smallest such subgroup where once you quotient G with that subgroup, you get an abelian group. Okay, so the smallest is important in getting the optimal approximation algorithm. Okay, so here is an approximation algorithm for if the instance is satisfiable and every constraint is like this. So here is an approximation algorithm. So let H be the quotient group, which is abelian. And now we convert equations over G to equations over H as follows. Suppose this is the equation over H. So I'm also using that, you can add constants in between. Although the hardness is also for the constants, which we could later. But you can also assume that the constants are more general. These are group constants and these are variables. So by convert, I will just have assign a new formal variable for each of the variables. X1 is like some formal variable Y1, and then replace the group variable by the quotient element from the quotient group. The respective. So these are like A1 8 variables. And 1G is like 1, and now this is an abelian, this is an equation over an abelian group. And you have a system of such abelian such linear equations. And the important point is that now this you can hope to find a satisfying assignment in polynomial time. And again, if this instance is satisfiable, then this instance is also satisfiable. That's easy to see. And furthermore, you can actually find a satisfying assignment in polynomial time because this is abelian. So once you find an assignment, it assigns some element sigma to hi, which is the coset of G, right? It's from the quotient group. And the algorithm is just assign a random element from this coset. So this was the assignment that you got for Y1. Now we want to find the assignment for X1. So you just assign a random element from that coset. Is the algorithm clear? So we use this abelianness to find an assignment, which is basically the set of possible assignments for a variable, which is from the coset. And then from this, how would you pick an assignment? You just choose a random element from that coset. And you can show that no matter what you pick here and what you pick here, there always exists one element from this coset that satisfies this equation over G. Okay, and that gives you 1 over Gg factor. And because the size of this coset is 1 over Gg, no matter what you pick here and here, there is one element in this coset that will satisfy this equation. So the probability that will satisfy this equation is 1 over the size of the commutator subgroup, and this is 1 over Gg approximation algorithm.
So okay, but just if in the stupid instance when, for example, the group was just the symmetric group, then in that case the commutator subgroup is
or the
Sn.
Sn.
It was Sn.
The permutation.
Then the commutator
Yeah.
subgroup is going to just be Am.
Yes.
And so each Yi that you have is either 0 or 1.
Yes, it will just give you the parity.
So this is like saying that if the parity was 0, you choose Z1 to be a random even permutation.
Right.
And in the
Yes.
other case, you choose a random O1.
Exactly.
Okay.
So that's why it was important that the quotienting group that we have, we want the size of that group to be as small as possible because the approximation factor we got is 1 over size of that quotient group. Right? And the commutator subgroup is the smallest such group where if you quotient it, you get another group. And that has to be the case because we have a matching hardness with the friend. So it's a very clean and nice algorithm. So what is it that got used in the approximation algorithm? So let's try to abstract out some property. So the abstraction is that whenever xy is a satisfying assignment, it satisfies some abelian equation over some abelian group. Right? What is this abelian group in this case? It's just the quotient group. We just map an element of a group through the respective quotient, and once we have that, whenever xy is a satisfying assignment, here I'm using the predicate where the constant is 1. It satisfies some under this mapping. It satisfies this linear equation over an abelian group. Okay, so that is what I call a linear property of a predicate. For every tuple in the support of a predicate, okay, no. So the quantifier is there exists an abelian group, so that for every tuple in the satisfying assignment, it satisfies a certain group equation. So let me state that formally. So a predicate P has a linear property if there exists an abelian group H and mappings alpha, betas, gamma from this domain to the abelian group H. So that, of course, we want at least one of the mappings to be non-constant, just so that it is some non-trivial. And then for every tuple in the set of satisfying assignment, we want the respective mapped group elements to satisfy the identity, some linear property. And now you can imagine how this can be useful, right? Because you can use this to find an assignment over H initially, which might reduce your search space a little bit. So instead of searching over this domain sigma, you might just search over some the inverse of alpha inverse of the group element from H that you have got after solving the system of linear equation over H.
So here your map is a homomorphic.
This map is a
Is a homomorphic map. It is going more commutative.
so that
That is a homomorphism.
that is a homomorphism, but in general
This
it's
is a
a
more general.
this is a more general definition. So this is the definition of linear property. I mean that we use in the book.
And I'm guessing that you're not just saying homomorphism because you get something more out of like having a more general.
Yeah, this may not be I mean there is no I mean sigma is just some domains. There is no group involved here. Right. So. Okay, so just an example, suppose this is your predicate and the same color things are like head of satisfying assignment except black. I mean, suppose this is satisfying assignment, this is satisfying assignment. Then this is an embedding of this predicate into Z5. I mean, I don't know whether you see it, but there are some numbers. And you can check that, if this is satisfying assignment, it satisfies 3 plus 0 plus 2 is 0 in this group and 1 plus 3 plus 1 is 0. Okay, so we want this to happen for every tuple in the set of satisfying assignment. Again, for SN, it was very simple, just a parity.
And we're not asking for an even or DF for anything, right? I mean, like,
No, it's not even only. It's just because for algorithm, only one direction matters.
but for the partner, you put,
Yeah, but okay, right. It's not even only. And this can be generalized to k predicates, same definition works.
Also, from your algorithm, this 1 over size of commutative seems is a very natural number that just comes out of it.
Yes.
Because a priori it wasn't clear to me how they will get that.
Yeah. So because because of the algorithm, it seems like that is a natural number. Yeah. But if someone just tells you that the hardness is 1 over digit, there is no way of knowing why this is. Yeah. Okay, any questions? So maybe I have to rush, or maybe I won't spend time on techniques that much. Okay, so let me tell you what our results are. So again, the question is, can we understand the approximability of satisfiable max CSP where the predicate has some structure? And the structure that we have is, we have a characterization for 3 every predicates that have no linear embedding. Okay, so okay.
And this is over any alphabet.
This is over any alphabet, any predicate. So give me a predicate, 3 every predicate that has no linear embedding, and then I can tell you, what is the best S for this predicate. What is the best
You explain what do you mean by that?
characterization? Yeah, I'll explain what I meant.
No, sorry. No linear embedding as in?
So this definition is
that thing.
yeah,
that
so
you
this is
just-
like this is saying that the predicate P has a linear embedding property.
Okay, this is the definition.
Yeah, this is it. There has to be one abelian group and one of the maps has to be non-constant because you could always assign all zeros, right? That doesn't give you any information about the predicate. So one of the mappings has to be non-constant, and then every tuple in the set of satisfying assignment has to satisfy the group equation. Okay, and if the predicate has no such embedding in any abelian group, then we have a characterization for clear predicates.
Now, how hard is it to prove a predicate does not have linear embedding?
Yeah, I mean,
Just brute force.
yeah, just brute force. Yeah. So
You mean brute
depending on sigma, depending on the domain size, you can put some bound on, what is the size of the largest abelian group if there is an embedding, and then you can use it.
and is 3 special?
3 special because the kind of technical and the kind of analytical result that we want to show, we could only show it for 3. So I'll just flash, yeah. So I'll state the analytical result. But yeah, the 3 is coming from that fact that we could only show it for 3, and it's actually we put forth the hypothesis that in general it is true for theory predicate. If that is true, then you would also get a characterization for theory predicate, which has no linear embedding.
And this is under UG.
So again, you can't have UG because we are only working with satisfiable instances.
But is it under NP or is it under some?
It's not
2 to
NP.
2?
It's some rich 2-to-1 games. There is also
So
some
it is basically a variant of UG which has perfect completeness.
yes, yeah,
That's your starting point.
yes.
Okay.
So again, the main thing from the algorithm is that linear property can lead to better approximation algorithms. That's what we saw for this lean max theory over the non-abelian group. And SDPs don't really capture Gaussian elimination because for max 3 lin or max 3 XOR, SDP, they can't do better than the random assignment sort of already. So they don't really capture the Gaussian elimination pattern technique. So our calculation basically says that for such predicate, whatever Bhangale characterization is, that holds. On satisfiable instances though.
Sorry, can you explain what we mean by SDPs don't capture Gaussian?
So SDPs don't capture Gaussian elimination, that is sort of like the belief. Okay. Because I mean, just to give you one concrete example, for max screening over C2, this is the usual XOR thing. I mean, here there is a very simple randomizer, the random assignment algorithm that gives you 1/2 approximation, and SDPs they can't beat this 1/2. Okay, but if the instance is satisfiable, you can actually do Gaussian elimination, right, to find a satisfying assignment. But even there, SDPs can't do much because you can find half one integrity gap instance. So SDP would think that the instance is satisfiable, whether the instance has only half a satisfying assignment. Okay, so this is what I mean by SCPs. They don't really capture linear property, and it's an informal statement. I mean, we are still exploring, what this statement means. But these examples they show that SCPs they don't have the power of doing Gaussian elimination in an informal sense. Okay, and that's why our result, we show that if the predicate does not have any linear embedding, then we can't really use Gaussian elimination sort of thing. I mean, again, that's like intuition. And then our calculation is that whatever LGD gives you, that's the best that you can do on satisfiable instances, assuming some conjecture.
So the characterization essentially take the same as DP.
Yes.
Whereas as DP,
Yeah.
find the best integrity gap.
Yes.
One essence,
Yeah.
and that's the.
Yes. Okay. So I won't go into techniques, just flash maybe the result. Okay, so the reason that why we could only do it for theory predicates and not for array is because of this main technical lemma that we show. Okay, so I'll just pass this technical lemma. So let's fix the predicate P and which has no linear embedding. So again, I have to tell you what the characterization is, but the characterization is just the Raghunathan characterization. So I'll have one slide which tells you the. But this is some analytical lemma that we show. So pick the predicate P which has no linear embedding, and let mu be the distribution which is fully supported on the set of satisfying assignments. Okay. Then for balanced high degree function, so f is a function from sigma to the
What
end.
is the fully supported?
Fully supported means it has full support on P inverse 1.
So its support is equal to P.
Is equal to, yes,
Okay.
is equal to P inverse 1.
Okay.
Okay. Then for balance, meaning that the expectation of each of the FGH, they are 0 according to the marginal distribution of mu. And they are high degree functions. Okay. Then this expectation, what is this expectation? You are sampling 3 inputs to FGH. So this is the input to F, this is the input to G, and this is the input to H, where each column you sample independently from this distribution. And then if these are high degree functions, then this expectation is really small. Okay, and this crucially uses the fact that P has no linear embedding. If P has a linear embedding, then actually we can come up with balanced high degree functions where this expectation can be 1. Okay, so that was on my previous slide, an example of why if the predicate has linear embedding, then how large this can be, and this theorem basically shows that linear embeddability is the only reason why this expectation can be large. As soon as your predicate P or the distribution we have has no linear embedding, for high degree functions this is small. So this includes the earlier result where we only showed this for some denser sort of predicate, but this gets rid of the denseness property. It just relies on the linear embeddability, and that is necessary. So if you have time, I'll flash that slide, but let's move on. Okay, so this is the characterization that we have. Again, it's just the Raghunathan thing. So suppose P has no linear embedding, and there exists an instance of max P CSP that has one S integrity gap. And we need some more technical condition. Then There exists a declared test, which is the gadget sort of thing in this reduction with completeness 1 and soundness S plus 8. So, and if you plug this gadget to this ratio to 1 gain, you get a hardness result. So any questions on this? Sorry, it was it was a bit rushed, but this is the sort of thing that.
So Aditya's question. So Raghav's result was a characterization.
Yes.
Suppose now you also get, so is that second thing on the, you need an integrality. If there is an algorithm, there has to be, there cannot be an integrality gap. Are you going to, we have a similar.
So this will imply the same thing, right?
It implies the same thing.
Because of the same design.
But you will also require this other condition on the SDP solution.
Yeah, so
The
we
local
require
distribution also.
every local distribution, the support of every local distribution, we don't, we want the support of every local distribution to be not linear. Because the way you sample the queries to declare test is by local distribution. And
Okay.
so again, I will
Yeah,
very
we'll
long about that, I won't go into that. But any question on this mainly?
So, so if you knew that your max is the PCSP that you have, the max PCSP that you have, somehow the predicate P does not have any linear.
Yes.
And in addition, the Raghavendra CSP that you obtain for this thing, the Raghavendra SDP that you obtain for this thing, you are able to find the 1, S integrality gap.
Yes.
Okay, then maybe I just don't know maybe what the and some
so
and some extra condition,
some
extra condition on top of that. Once you have that, you are able to recover Raghavendra's result where you don't lose anything on
where I
the.
don't lose perfect.
Okay.
Yeah, where I don't lose the
Okay.
Which means that this hardness will applies to satisfiable instances, right? Because
I see.
I'm not losing epsilon in the completeness thing. Right. So 1s translates into 1s plus epsilon hardness.
Okay.
Sorry, so, I mean, what is that extra constraint saying?
So SDPs give you for every constraint involves a tuple of 3 variables, right? So SDPs, they also give you some local distribution on these 3 variables, on the assignment of these 3 variables. And we want that every local distribution that, and various constraints, they have their own local distribution, right? So this condition says that local distribution, the support of that has to be non-linearly embedded.
Okay. So if you, this naive question, if you remove this part,
Yeah.
you don't have that on it, like maybe some constraint, then
No, then
is there something that you can recover from it?
No. Yeah, so I'll be happy to explain, why we need this condition, but after that. Okay, so again, I wanted to spend some time on this result and one application. So this result says that, so the earlier result says that if it does not have a linear embedding, then that expression is small. If I give you something of that expression, and if it is large, then what can you conclude about those functions? So the stability result says that, give me any predicate and you will be fully supported on P inverse 1. And again, you are interested in evaluating this expected value of this product. And if this expectation happens to be large, then what can you conclude about this function f? The thing that you can conclude about this function f is, f looks like a product of some specific linear specific function. So f looks like a linear function times a low degree function. So again, if P is not linearly embeddable, we know that this expectation is small. If P is linearly embeddable, then the only reason this expectation can be large is it looks like the example that I have on the slide, which I skipped. But the example is like essentially so the example is essentially a linear function.
Here, by low degree function, because it seems as if product of a linear function and low degree function is also low degree. Here, low degree you need it's -1 to the power a low degree function. So it's
but the linear function I mean is in the Fourier world low degree. So maybe it's important to flash that. Okay, so let's say P is a predicate which is linearly embeddable. So then we take that predicate, which means there is a group such that, and there are these embedding alpha, beta, gamma. Okay, right? And let's say chi be any non-dual character of H. Okay. Okay. Now from this, I'm going to construct three functions, G1, G2, and G3. Okay, what are these? They take this n very the input, and they just apply this character to each of the. So you apply the map alpha, you get a group element, and you apply the character to this group element. You get it for this, you get complex numbers, you multiply all these things. So that's how I define my G.
Yeah.
G2 is similar and G3 is similar. So again, these functions are high degree, right? Because
Which functions are?
all these functions are high degree.
Yes.
Again, I did not define the notion of high degree.
Because this multiplication is happening in the complex.
Yes, this multiplication is happening in the two real complex,
Yeah.
complex one, right? And now, if you sample XYZ like that, where this is supported on P inverse 1, by multiplicativity of the character, you just get chi, at each coordinate, you just get chi evaluated as this sum because of the linear embeddability property. And not because of the linear, this is the multiplicativity of the additivity of the character. And because of the linear embeddability, this is 0. Right? And you just get 1 here if you evaluate it on here, where each column you sample it from P inverse 1. So this is one reason why this expectation can be large if P is linearly embeddable, and the stability result says that this is the only case. So P has the function G has to look like this linear function, which I call the linear function, times a low degree, because even low degree function they have this property.
Prefer you don't call it a linear, you call it a character.
Yeah, character.
Because linear into low degrees is
Right,
low
right.
degree.
Yeah,
It's a character.
it's a character times. So
Character.
that looks like a character, high degree character, or doesn't matter, and then a low degree function.
Yeah.
So, okay. I mean, so I'll just take one application of this stability result, and this is related to arithmetic progression. So fix your fix FP to then for some time P, and fix a subset A of that. A three-term arithmetic progression is a tuple of the form x plus 1, x plus 2, 1. Okay, and where y is non-zero. And we are interested in how small can A be to avoid any three-term arithmetic progression. And Roth and Mechelon, they show that the size of A has to be at most P to the n or into this. As soon as you have a subset of size larger than this, it has to have one non-trivial A at least. And recently, Ellenberg and Fujit improved this to the exponential power 2.76 to that. And okay, so then we know this thing about the arithmetic progression. We can study restricted arithmetic progression. So what is it? Again, the same setup. You are interested in finding an AP where the difference is now restricted. So I don't want any y, but I want y to look like 0, 1 to the n. So the shifts are restricted in some sense. Okay, and then you can ask the same question, how small can A be to avoid any restricted three-term AP? And the only thing that we know follows from the density Hell's fluid theorem, which says that A can be at most P to the n over log star n. That's the only bound that we know, and that just follows from the DHA theorem. So ideally, and the DHA predicate, you can think of DHA theorem as you have this predicate where the tuples are all A's and 0, 1, 2, 3 up to P minus 1. So in DHA, so I won't define DHA, but it looks for here we are looking for AP. In DHA, you are looking for some combinatorial line. And if you look at the structure of a line, then every column you just see either the same element or 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6. Okay, so this looks like you're sampling. So we could not actually show it for that restricted three-term AP, but if you could just extend that or like loosen that restriction a bit. So here we are interested in the same problem where the shift is from 0, 1 to the n. And then you can ask the same question. Again, DHA theorem says this, and we show using our stability theorem that A is at most some fixed log n to the power. Okay, and where is the linear embeddability and everything coming into picture? So here the predicate is actually, so if you look at this arithmetic progression, if you take any three such tuple from that restricted AP, if you look at this, the support of that looks like this. So X is from FP and A is either 0, 1. because it's xi, x plus yi, and x plus 2 yi, where yi is either 1, 0 or 1 or I think that is, yeah, A is in 0, 1, right? And that predicate, so that predicate has linear.
So here P is not 3.
Yeah, P is some large time.
Here.
And this predicate has linear embedding. And again, I skipped that out for our stability result. We want P to have linear embedding, but no C embedding. C is like integer embedding. For some technical reason, we also require that. So this predicate satisfies all the properties that we needed for the stability result. Okay, and the argument is really similar to the Roth's theorem. This expectation is large, which means F is correlated to the product of the character and this. That tells you where to move, where the density increases. So that is the meaning. I mean, that's how that's one way to look at the stability. It lets you move to a smaller region to increase the density, and that's really there is in this paper.
What is the region?
So the region is so F is correlated to this character times probability, right?
Right.
So the character only takes some finite number of values,
Right.
because it's a finite group, right?
It's like a region in this table.
No, so character, if you look at output of the character, it just takes some
Right.
the G many values, or depending on the availability.
Right.
And that split the space into those.
By region you mean
So this is like a concept of entry design. These are all the points where that
Take the fiber of the.
yeah, the fiber. So you move to one of these. But again, I mean, this makes things complicated because there's a loading part, you have to get rid of that. And that makes the density argument a little bit trickier, but essentially we use that stability result to do the density increment argument. And really the point is this. This correlation gives you a way to move to a smaller space to increase the density.
What's the work? Is there a variant type?
So yeah, so no, so it's so people believe that you can show something like P minus epsilon to that.
Like
So it's like the unrestricted PA. And the reason we could not show it for that only 0 1 restriction is that if you look at the corresponding predicate, it has a 3 embedded.
So even in the restricted setting, when you're only looking at the differences to be
Right.
0, 1, 2 to the end, the belief is that
Yes.
even if your set is like as large as P minus epsilon to the
Yes,
end, you should
it will
see.
have. Yes, that is the belief.
Okay. Okay.
It's far from being. Yeah, so as I mentioned before, so if you just focus on this restriction, the reason we cannot get it for that is if you look at that predicate, it will satisfy, it will have a V embedded. You just write down the equation, and then the matrix is in non-invertible, and then you can have a Z like embedding into the integers. And our stability result only works for predicates that have no Z embedding. So yeah, that's it. So again, the open problem is the technical lemma that I flagged that for every high degree function, the expectation is small. Can you show it for in general theory predicates that are not linearly embedded? So we have to show it for theory predicates that are not linearly embedded. If you could show it for this will sort of characterize every theory predicates that have no linear embedding.
So by high degree, how high do you mean?
High is like so as you keep increasing the degree, this factor should go down.
Okay, so there's a trade-off.
Yeah, so this is little over 1 of the degree. And the one open problem is, design approximation algorithm for satisfiable max PCSP, and here somehow we need to combine Gaussian elimination plus the recipe rounding algorithm in some clever way. At least that example of max Euclidean or non-abelian group, we combine Gaussian elimination and dynamic rounding. But maybe in general, there is a way to use recipe as well as Gaussian elimination together to get the maybe the optimal approximation algorithm. So we don't know this yet. I should stop. Yeah, sorry for it.
Questions for Amey?
Linear embeddable doesn't.
Okay. So this definition is tailored to they think that once you have this, it should somehow help you in getting some good assignment. Because you could solve the system of linear equation over this, or the group H. And that instead of like sampling a random element from sigma, which is which is an algorithm, this lets you go to a smaller space and maybe sample from there. If you have
And the like one concrete instantiation of this was that you quotient, if you start off with a non-abelian thing, you quotient out with the commutative subgroup, and then you end up with an abelian.
right.
And there now you can sample randomly from.
Yes. So they are just sampling randomly from this group, from this quotient with respect to quotient. That works, and that was optimal.
There the alpha beta gamma are the same thing.
Right, their alpha beta gamma are the same. Their random sampling gave you the optimal, but in general, maybe you need to combine this with some STP routing.
So these papers, there are already 4 papers out
Yeah.
there, no?
Yes.
And the lemma you flashed is in the final paper.
So the stability one is in the paper number 4.
Paper number 4. So what's these papers? All these papers on the look of it are heavily technical
Yes.
papers. Do you have? So is the final conjectured lemma the brief statement that if you had to prove the result?
It will prove the result for predicates that have no linear embedding. We still need to work.
Oh, you need to still work.
We still need to say something about predicates that have linear embedding, and now Gaussian elimination and STP. But
And you have more papers in the
so we have paper 5 where we combine Gaussian elimination and STP to give you an optimal algorithm for very small class of predicates. So there the statement is not like as general as this one. This is a very clean condition. P not having linear embeddability. There we need the predicate to satisfy some symmetric property. Then we can show that the Gaussian elimination plus STP is sort of optimal for that predicate.
But in how far do you think we are from the full characterization?
So the 4th thing looks like Gauss thing. So showing 3-term AP bounds, it was not difficult. But then showing 4-term AP bounds was like, the difficulty was like shoots up as you go from 3 to 4. And we believe the same reason is there. These theorems, they look similar,
Okay.
So and that's the difficulty. So that's why going from 3 to 4 looks like a big jump. But once maybe
What are the difference between Ross proof and Gauss proof?
Exactly.
Similarities there.
Yes. Because there are many other examples, some quadratic things where the expectation is large, right? That was the same. So only linear functions, they are not able to capture the expectation being large, the correlation for 4AP. For 3AP, those are the only things. But for 4AP, there could be other weird functions.
That's because you're going a very Fourier analytic approach. Whereas in the case, the other one, similarity has both the 3AP, KAP here.
Yes.
He has
he has
other proof,
right.
which is the regularity lemma.
Right. So that we don't know. Yeah. So
There is no corresponding such proofs over here for.
Yeah. So there is no.
You are being disconnected.
Oh, yeah, it's connected.
Okay.
Okay.
Other questions from Amey? Let's thank Amey. Amey will be around for most days or until the end of this month.
End of the month. Yeah.